Thank you. Well, as you probably said, my name is Henrik Andreasson. I don't understand a word of Estonian, so I will take this in English instead. I'm working for a company called Profjord, which is a small company focused mainly on hydrodynamic design, and our main competence is within the hydrodynamics. So we are developing and designing hydrodynamic solutions and design. And before working for Profjord, I was working almost 10 years at SSPA model base in Gothenburg as a project manager, and so therefore I have a lot of experience from evaluation and preparations of a model test. And I graduated from Chalmers University of Technology in 1999. Start to be a long time now. And since then I've been working within the hydrodynamic field. What I'm planning to talk about today is, I'm asked here to come here and talk about hydrodynamic design and hull design. I will not go into detail into specific hull types or specific designs made or so on. I will try to cover a bigger picture of how it starts with deciding of parameters and the importance and the couplings of parameters and what impact they actually have on the final hull. And I will talk about this. This is small craft, often quite high speed. Trim is essential for the performance of the boat in many aspects, not only for speed performance. I will talk about the dynamic stability and importance of how the hull looks also above the waterline. There is an idea of hydrodynamics is only underneath the water, but when we're operating heavy seas, also the hull above the waterline has a great impact on the performance of the boat. We'll talk a little bit and bake it together, how we evaluate it by model test and safety analysis until sea trial is the final test. And then I will talk about the impact of propulsion arrangement to the hull design and how it's judged, what's possible to make for design. And also the steering arrangement, which is quite coupled to the propulsion arrangement, has a great impact on how boat behaves while maneuvering at high speed. And then I try to squeeze in a little bit about designing appendages for high speed when we're reaching speeds above 40 knots. First of all, I just want to show you some examples of what we have been involved in. This is a lightweight rescue runner made of carbon fiber, built at Swedish ship for Norwegian rescue service. It's capable of 37 knots, 2 times 330 kilowatts. So this is a quite small rescue runner, and on the opposite we have here a very heavy boat. It's Odin. It's 24 meters. It's about the same size in length as the KBV 312, for example, or a normal, like a normal patrol boat, but the weight is about 95 tons on this one. It's very comfortable in heavy sea state in high speeds. It's reached about 28-29 knots, propeller driven with CP propellers from Helleset. it's a big, a good working platform for, and it's planned to be operating in the North Sea. The KBW 312, we made the hull design and adaptation to IPS propulsions and optimization of the hull. We also work a lot with small crafts. This is the smallest we have been involved in. It's a design made of Mikkel Selenius for reeds, where we were responsible for the hydrodynamic performance of the boat. That one reached 40 knots about with 90 horsepower outboarder. And we've done some designs for Brandskär 29 and 31. And we've also been working some Italian yachts. This is a Mangusta 130, which is a 40-meter long pleasure boat, reaching speeds about 40 knots. And they have, this one is the biggest sister, it's 50 meters, reaching 43 knots with 3 times, well, it's about 10 megawatt installed power on that one. Weighs only 250 tons. We design hulls, and then we using CFD calculation in the initial phase to optimize the hull shape, and depending on the budget for the project, we also survey and plan a model test and evaluate the results from that. Now, to what I'm supposed to talk about is the first thing I mentioned in my list of today's speak is the importance of choosing the optimum main particulars. And I just listed up main particulars that are known to a different degree. Length of roll, beam overall, and draft restriction is often very clearly defined. Displacement and LCG, VCG is something that develops out from the construction and moves around a little bit during the design spiral. But it has a great impact on the performance of the boat and on the choice of for example, which type of propulsion arrangement that is possible to use for it. Metacentric height, how stable do you want the boat? Is it, you could think that, oh, I want it as stable as possible because then it's a good platform. And a good example of that is a boat like the first one. They often tend to be quite stable, open, small boats. And if you are out in some waves with such, it moves very quickly, at least if it's heavy compared to the crew. And the feeling you get from it, it is stable, but the response of the boat is so rapid, so it feels uncomfortable. But that also something that depends on who is using the boat, because some people want the boat to roll a lot. Different crew have different aspects of what is enough stability. So that's something that you have to have to take into the design process, what the client is expecting. And often that is referred to reference vessel. Transom draft. If you come to semi-displacement hulls, which is not really planning, transom draft is a key to be able to reduce the resistance. Transom draft is how much of the transom that is submerged. Propeller shaft RPM, which RPMs are available, and what propeller diameter could we fit into it. Product chain area and distribution is coupled to the GM, the stability of the boat, and how responsive do you want the boat to be in a certain sea condition, and how stable do you want it to be. Should you be able to handle to lift aboard cargo outside the hull and so on. hard shine or round bilge hulls. Nowadays it has become more popular with round bilge hull designs, not only for catamarans but also for larger, not for a patrol boat maybe, but a little bit larger vessels that's operating in 20 knots.
Then I have a question. Why?
Well, it's interesting to look on it. Or
No, but why run bilge?
why run bilge? It's if you're in the subplaning regime, you could say that hard shine costs you about 5 to 10% in added resistance if you're not using it as a. But then again, it offers something else. It offers roll damping, for example. And if you make a round bilge design, then you often have to compensate with bilge keels. But bilge keels is possible to align in the streamlines, which the shine isn't. It depends very much on what speed area you are in and how much the wave resistance is on. But there are definitely cases where round bilge are superior and where it's much more than 10%. Shine beam dead rise is something that when coming to faster, smaller boats is often used as describing why a boat is good or why it's not so good. But I would say that it's not that very important. It's a coupling in between all these parameters that makes a good boat, not the dead rise angle or bottom angle. There's also other aspects. If you're going to operate the boat in a very heavy sea states, for example, and it's likely that you operate in following sea, then you don't want to have these very full beams, which are quite popular today, because then you will have increased risk of broaching. But that's something that has to be taken into account when you set up your project. I'm going to show you some examples here of what the consequences are of parameters. Here we have a graph of effective power, which is a measure of needed installed power. It's the towing required power to tow the model or the hull. And on the x-axis we have the center of gravity in longitudinal direction. And this curve here, the continuous line is one beam. I think in this case it's 3.5 meters, and this is 10% smaller beam, and this is 10% wider beam. And the optimum combination is of course where the resistance is as low as possible. But we can also see that depending on which beam we use, or depending on which LCD we have chosen, we have slightly different results. But we can also see that if we are close to the optimum, then it doesn't have that very great impact on the resistance. But if we for example, already are here, or that line, and chosen to increase the beam to increase stability of the boat because it's needed. Oh, the opposite, sorry. Decrease the stability of the beam for some reason. Then the drop in efficiency is quite severe. And what's worse is, and what is quite common, that you design the boat for 35 knots, but in real life you're operating in 25 knots. Then you're quite far from optimum. This is valid for a planing hull from quite monohedron type. There are some rules of thumb saying that a planing boat should have an optimum trim of 4 degrees, and then it's operating at normal. as optimum as it could be. But we can also see here that depending on which speed we are operating in, and this is of course related to the displacement of the hull. You can see that here on the x-axis we have the trim, and here we have the effect, and we see that, well, if we are in the low speed region, 25 knots, this is about 15-meter long boat, so it's still quite high speed for such boat. Then we have an optimum, which is quite much smaller than what it is if we increase the speed. But depending on the parameters we choose, what's the optimum trim is very variating. And that could be good to bear in mind. I was talking a little bit about the importance of transom draft, and here is an example from real life. It's rescaled, but the displacement of this is these three ships here are about 300 tons, and the characteristics could be characterized as semi-planing hulls. And we can see here that we have one hull here which has a very small transom area, it's about 20%. And, this green line here has about 50%, and this blue line here has about 90% transom area. What I mean with transom area in percentage is a measure of the maximum section area compared to the area submerged transom area. So it's a measure of the distribution, and of course this will then naturally have a consequence of the possibility of moving the LCG. But we can see here that if we design something for 25 knots and uses this hull here, which we know was so good when we operated at 40 knots, then we have a tremendous drop in efficiency. Now, it could be other reasons why you can't do this, like if you have an accommodation area which is very light and have very heavy engines, you cannot do very much about the center of gravity if you have chosen that you want to have water jets because you are comfortable with water jets, or that you see other benefits. Draft restriction can be there. But this is as much as it is all about. So it's not small things, but it requires also that you have the possibility to achieve this combination of parameters. All these ships are built and successful in their operation. And they were not designed for the same speed range. But it's a little bit interesting if you pick one of these boats and start to elaborate a little bit what's happening if we move. We have one certain hull shape, and we elaborate a little bit with the center of gravity. We trim it on the bow. and we can see that we have a should explain this graph here. Here we have the speed, and here we have the resistance in relation to the chosen parameters, or the actual parameters. And if we shift the center of gravity forward, which is about 4%, this line here, we have in the low speed we have a quite big gain, but we have a crossover when it's not so efficient anymore. This curve here is showing how much a knot cost, or how much you have to reduce the resistance to gain 1 knot. So if you're in the 20 knot regime or region, you need to have a resistance reduction of 8% to be able to gain 1 knot. But if you are in 35 knots region, then it's enough with 5% gain. So resistance reduction is because normally we measure the performance of the boat in knots. We don't measure it in fuel consumption, or not to that same extent at least. But depending on where we are in the speed range, it has a great effect on what we can achieve. I was pointing on the wrong curve. I mean, 11% at 20 knots and 5% at 35 or 40 knots. Sorry, but so it's very big difference in how much speed you gain depending on your resistance reductions. And here is if we, instead of moving the LCG, work with the scoop of the aft body and able to create or balance a hull, we can adjust the hull lines to lift the stern. And we can see that compared to moving the LCG, which is quite often not possible or very difficult at least, we can gain quite a lot with adjusting the hull design. This is made with interceptors or trim, or could be trim flaps, but it's to be able to reach such figures you need to have a very wide area of the transom covered. This figure here I included to show you why it's so important to take care of the back to design the stern. And often the most of the designs existing today have quite slender forebody lines, and that's a lot of focus on the forebody. This is a CFD plot of the wave pattern of a larger semi-planing hull, where blue color shows a trough and red color shows a crest of the waves. So if you have a lot of different colors, then you have higher waves, and if you have less different colors, then you have smaller waves. And this is the same hull, but just adjusting the scope of the stern, which lifts up and reduces the trim. What's interesting with this picture is that you can see the balance between the wave pattern from the bow compared to the wave pattern in the stern. And you see that this region here is very much more creating higher waves. And with high waves, there is a relation to that, to the resistance. If you create small waves, then you create less resistance also. And we can also see the difference between the lower half and the higher half, how much you could actually affect it by small adjustment to the hulls. This picture is pretty much showing the same thing. We have the resistance curve here, and we have different trim tabs settings here. But we can see that by this is a classic monohedron hull, the red line here, and then we have a different amount of interceptor deployment. And we can see in the lower speed gain we have a lot of gain in the resistance, but in the higher speed gain it's better to have them off. So there is a reason for having variable trim tabs, especially when you come over to the planing regime, where you come to a point where you want to lift out the hull out of the water. If you're in the lower speed regime, then you can, or region, then you can incorporate into the hull design. But so you have a pressure build-up in the stern that keeps the boat in a level. But then you could say about length through number about 1.2 or something. You want to start to lift up the bow in order to reduce the wetted surface area, because then the frictional resistance becomes more and more important. if we plot the trim to the same in the same graph, we see that we had benefits of hooking the stern up to 25 knots. And you can see also that this is about much less trim in degrees than these 4 degrees. But then when we want to go really fast, then we want to lift the hull out of the water. Also showing a slide. This is a similar slide, but this is for catamarans. And catamarans are quite interesting because you have interference in between the hulls. So often you often have a much more slender hull compared to a mono hull for the same weight. But on the other hand, you have the interaction in between the hulls that you have to handle in some way. On the outside, due to the slenderness of the hull, you often have quite small waves. But you can see here that this bow wave you have here will interact with a maybe it's a little bit dumb here because I took two different, but if you imagine that it comes a bow wave from the other hull here, which is located at the same point, you see that you will get an increasing wave height at this point where the waves meet. And this is especially true for this rig in here, the aft shoulder, where this is a propeller hull, so where you lift up to make space for the propeller, you get like a spoon shape, and this spoon shape is well, like you take a spoon and hold it into water, it sucks into the tap water, what do you call it, waterfall. Yeah. So this is creating a low pressure area, and everything gets exaggerated. In this example, we worked with a bulbous bow in order to get these waves damping out. But by having a bulbous bow, you get a bigger a length where you don't have reflection, and in that way you could reduce the interaction between the waves. Impact of propulsion arrangement to the hull design. I said earlier that it's very effective for if you're talking these boats that are quite slow compared to the size of the hulls. It would be very beneficial to lift the stern, but if you have these type of big water jets, it's not really possible to lift the hull because you have must fit the propulsion somewhere. And this is a picture of the KBV 312 where we were allowed to raise the transom, much because of that we had to fit the IPS units within a draft restriction. But that's also beneficial from resistance point of view from the operational profile for this boat, which is operation mainly in 25 knots and able to reach 30 knots. And if you take open shaft propeller arrangement, for example, then you need to lift the transom even more because of one benefit with the IPS units is that they are counter-rotating propeller, which means that you can reduce the propeller diameter. But if you go to a twin prop arrangement, then you need to, as the propeller are quite large, you need, including the clearance, to lift the hull quite a lot. And you come to a point where you lift it too much to gain for it. So the optimum choice of propulsion arrangement is based on many things. This picture here shows the pressure distribution where we have a hook in the tunnels and a center part of the hull which generates a lifting force further aft, and but that has to be counterbalanced by this low pressure region here, because we need to raise the stern able to create the tunnel. And then this will generate a low pressure. If you increase speed, this in semi-planing speed, it's very efficient to do like this, because then the transom resistance is quite high. But as speed increases, this will mean that you will suck down the middle of the hull, so you will not lift the hull as much as you would do if you choose a more monohedron hull design. Impact of steering arrangement to the hull design. This is the rescue runner I showed in the first picture doing a turn. And this boat behaves as you want. When you're standing and giving the full wheel, a tight turn, you still have the acceleration straight through the deck. So you don't get a lot of side forces while turning the boat. And that you could call coordinated turn. That you heel the boat to balance with the turning radius, so you get less side forces on the crew. When you if you would make the boat more stable by increasing the beam, it would go more upright through the turn, like a tram. And you would have to, for this guy who steered the boat, that's maybe fine because he has a wheel to hold in, but for the others it's could be a mess. If you reduce the weight center of gravity in vertical direction, you will heel the boat more inwards. This is a picture I've borrowed from Principle of Yacht Designs by Lasse Larsson. But it's a good picture. Here, when you do a turn with the hull, you have some kind of rudder. It could be water jet buckets, or it could be a regular rudder or IPS unit, doesn't matter. Which generates, you want to turn the boat in that direction, but it generates a rudder force in the opposite direction that will start to rotate the hull. And when you rotate the hull to the flow the hull is meeting, you get forces from the water passing the hull, pushing the forebody of the hull in the right direction. This is what makes the hull heel outwards, mainly. This to some degrees, but this is. I will make this arrow a little bit longer. But you also, when you do a turn, you have centripetal forces. Want to heel the boat outwards in the turn, and some flybridge boats suffers from this when you have a high center of gravity, which heels the boat outwards in the turn, and that is compared to the tram turn, which is not so nice. Such turn is really scary. And there are existing hulls that in production that behaves like that. And this is coupled to many things. One is, of course, as I said before, the height of the center of gravity. If you move it up, then it will turn outwards. If you move it down, it will turn inwards. But it's also so that depending on how willing a hull is to turn, it will, if you make a tight turn, this centrifugal force will be stronger. And if it's a slow turning hull, then you will have a lot of rudder force, but nothing happens. So, I mean, there are examples of boats going straight ahead. So the only thing that happens when you turn the wheel is the boat heels. And and then you have a force from the rudder heeling the boat. But that sounds quite strange. Why doesn't the boat turn? I mean, if you have something in the back pushing the boat stern in that direction. Well, if you have been out in a small boat with an outboarder, and you step forward in the hull a little bit. You could actually steer the boat by heeling the hull, but you do not steer like this. You steer like this. So that if you heel the boat, the hull would like to steer in that direction, but the rudder will try to get the boat to get in that direction. So that if they counterbalance, nothing happens and you go straight ahead. And to many hull designers are very afraid of the broaching behavior of a boat, so they tend to lift the bow a lot. But what could happen then is that you don't have nothing that steer the hull when you add this side force from the rudder. So then you get poor steering ability. On the other hand, if you have a deep bow or vertical stem, you can have very good steering ability if you manage to push it down. But in following seas might not be so nice. So it's a matter of balance. What is the time? I don't have any watch. 12:30. 12:30.
All is okay. You have
Okay.
20 minutes.
You have to. If I bore you out, you have to interrupt me, because I can speak for ages about this. Dynamic stability and the importance of hull design about design waterline. First, just listing up what different types of dynamic instabilities there are. The most common term is maybe porpoising. That is when the hull starts to trim oscillating up and down. And we jump a little bit in the. Then we have shine walking, which is a little bit the same thing, and but in the transversal direction, that the boat oscillates like this. And then we have shine riding, that the boats find another stable position at a certain heel. And we have bow steering. I said earlier that, and from my presentation you can judge that, well, it's just to trim the bow as much as the boat as much as on bow as possible, then everything will be fine. Often you run into that you increase performance, at least for semi-planing hulls, by trimming the bow down, but the steering starts to be a little bit of uncomfortable. The boat feels like the boat steer away a little bit like itself wants to, and so normally you want to raise the trim a little bit further to have a good handling of the boat. And then we have a quite extreme form, which is bow diving, which is similar to what we talked about before, with a spoon sucked into the waterfall or tap water. If you have two curved hull lines, you get a suction force that trim the boat on bow, and the consequences can be quite dramatic. Porpoising. There are porpoising criteria. Quite old one put up by Savitsky. But you can say that porpoising is something that occurs when compared to the speed and displacement, but when the trim is raised too much. And the reason why you raise the trim is in the high speed region where you want to lift out the wetted surface area. But if you can, you often find in the planing regime that when the boat is well up and planing, in the same way as in the semi-planing speed region, you gain in trimming the bow down until you're not able to steer the boat. When you increase the speed above and fully planing, you will notice that the more you can trim the bow up, you will increase the speed performance until the boat is starting to get dynamic instability. And the same is a little bit with shine walking. It's related when you have lifted up the boat so much out of the water that it doesn't have very much of stability left. Then it starts to occur. This is a graph summarizing it quite well, where we have in a longitudinal direction porpoising here, shine walking here. We are in the fully planing region. And in lower speed region, it's not so likely that we have shine walking, or porpoising, but here we might have trimmed down the bow too much, so by hull lines or by trim devices. So we will have bow diving effects, or that the boat steers away on the nose, or that the boat heels due to dynamic forces.